All right, in today's lesson, you are going to be learning how to draw Bohr diagrams. So the Bohr model is a specific type of model that shows all three types of subatomic particles. It shows how the neutrons and protons are located in the nucleus of the atom and how the electrons are arranged in orbits surrounding the nucleus. And there is a certain number of electrons that fit into each orbit, and how these electrons fit in and the numbers of electrons that fit in specifically in the outermost shell, which we call the valence shell, that really is the basis for all the properties that the different elements have and how they react chemically. And you'll learn more about that in grade 10 science, as well as if you take chemistry, grade 11, and chemistry grade 12. So our task for today is to learn how to draw a Bohr diagram. And you need to be able to draw a Bohr diagram for the first 20 elements. So the easiest way to do this is to show you by an example. On Friday, you will be practicing drawing these Bohr diagrams for all the first 20 elements. So we'll begin. To draw a Bohr diagram, we need to do the following. We need to first of all figure out what the atomic number is and the mass number, and we make sure that we round it. So we are going to draw the Bohr diagram for a single atom of fluorine. The first thing we need to do is go to our periodic table and find fluorine. Oops. Okay. So we look and we find fluorine, and there it is. It's element number 9. It has a mass number of 18.998, so we'll round that to 19. So atomic number 9, mass number 19. The next step is to determine the number of subatomic particles. So the protons, the electrons, and the neutrons. Remember that the protons and electrons in a neutral atom are equal to each other, and they are equal to the atomic number, which is 9. So there are 9 protons, there are 9 electrons. The number of neutrons is the mass number, in this case 19. Subtract the atomic number 9, which leaves us with 10 neutrons. So this has been drawn for you, but the first thing that you would do is that you would draw a circle, okay, that represents the nucleus, and you would write the number of protons and neutrons inside. So 9 protons and 10 neutrons. The next thing we're going to do in step 3 is determine the number of orbits. And so there's another name for this. They're also known as electron shells. Okay. So there is sort of a pattern here. The first shell, we can fit 2 electrons. The second, 8. The third, 8. And the fourth, 18. Now, in case you forget this, here's a little tip. If we zoom out, okay, too much. If you remember the vertical rows, okay, sorry, the horizontal rows, vertical rows. The horizontal rows are called periods, and there are 7 periods. So on a Bohr diagram, whichever period the element is in, that's the number of electron orbits it has. So fluorine is in row 2, so it would have 2 orbits. So that's how you determine the number of orbits. So for example, tantalum, element number 73, is in period 6, so there would be 6 orbits or 6 shells that surround the nucleus. Now, back to the number of electrons that fit inside each shell. It goes 2, 8, 8, 18, 18. How do we know this? Well, you can count the number of elements in each row. The first row has 2, hydrogen and helium. That means 2 electrons fit in the first shell. The second row has 1, 2, 3, 4, 5, 6, 7, 8. So in the second row, you can fit 8 electrons. The third shell 8, the fourth, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there would be 18 in the fourth, and there would be 18 in the fifth. And now for grade 9, you don't go past element 20 for assessment, so you wouldn't have to worry about row number 7. But again, you would just count the number of elements to fit. So that's sort of how that works. So we'll go back to our example, and we'll realize here what we do is we draw the number of shells. So remember, fluorine is in the second period, so period 2. So therefore, it has 2 orbits. 1, 2. All right, so we draw them, okay, surrounding the nucleus. And the next thing we do is we fill in the electrons with dots. So we draw the electrons as dots on the orbits. So we always start from the innermost. So 1, 2, okay. Once an orbit is full, move on to the next. Work your way out. So the second orbit can fit 8, but remember, fluorine has 9 electrons. And if we've already filled in 2, there's 7 left. So 1, 2, 3, 4, 5, 6, 7. And if we count this properly, there should be 9 in total. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this, inside the box, is a Bohr diagram. Now it's worth noting that the outermost shell, okay, so the last shell, in any Bohr diagram, the last shell is called the valence shell, which means outermost. And therefore, the electrons found in the valence shell are called valence electrons. And these electrons are very important. They sort of form the basis for chemical reactivity. And you'll learn a little bit more about that in grade 10. And certainly you'll learn more about that in grade 11 chemistry. So we'll go through another example from scratch to see how we can draw a Bohr diagram. So here we're being asked to draw a Bohr diagram of a single atom of magnesium. So magnesium, remember, is symbol Mg. Okay, so we need to know the atomic number, and we need to know the mass number around it. So we go to our periodic table, find Mg, which is element number 12. Please zoom in here. Take a look. There it is. Element number 12, and its atomic, mass number is 24.305. So we would round that to 24. So atomic number 12, mass number 24. And we may as well figure out what row it's in. So the row number for magnesium, it's in row 3, or period 3. So it's going to have 3 electron shells. 3, therefore 3 electron shells. Okay. Now, back to here, we need the subatomic particles. We need the number of protons, we need the number of electrons, and we need the number of neutrons. So remember, the protons and electrons are equal to each other in a neutral atom, and it's equal to the atomic number. So 12 protons, 12 electrons. Neutrons is equal to the mass number, 24 minus 12, which means there are 12 neutrons in the nucleus. So the first thing we'll do is draw the nucleus. I'll draw it in a different color. Okay, so I'll draw a little circle, and that's nucleus. So inside the nucleus, we have the neutrons and the protons. So we have 12 protons and 12 neutrons. So make sure you label that inside the nucleus. And next, I'll do it in a different color. We will draw in the electron shells. So there are 3 electron shells. Do your best to draw 3 circles. 1, 2, 3. And now we fill in the number of electrons. So we have 12 electrons to fill in, and we start from the inside and we work our way out. Remember, it goes 2, 8, 8, 18. So 2 fit in the first. So we have 12 electrons minus 2. So we can keep track this way. All right. So we can definitely fit 8 more in the second shell. So 1, 2, 3, 4, 5, 6, 7, 8. 10 minus 8 is 2. And that means there's 1, 2 electrons left. So if we count up the number of dots, so it's a bit bigger so we can see them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons in total. And just for learning, the number of valence electrons would equal 1, 2. So there's 2 valence electrons in the outer shell. Interesting, if you look at magnesium, it's in group number 2. So the group number tells you the number of valence electrons. Except for when we get over here, 13, 14, 15, 16, 17, 18, we actually have to subtract 10. So boron would have 3, carbon would have 4, nitrogen would have 5, oxygen 6, fluorine 7, and helium, and the noble gases, they would all have 8 in their outer shell. So this summarizes how we draw Bohr diagrams. Again, as a review, we locate the element on the periodic table. We write the atomic number, the rounded mass number. We determine the number of protons, electrons, neutrons. We find the row number, and we draw the correct number of shells. When we do that, we draw the nucleus first, write in the number of protons and the number of neutrons, draw the 3 shells, or however many we have to draw, and then fill in the electrons as dots. This concludes our lesson on drawing Bohr diagrams for neutral atoms.